In this video, I'd like to discuss the difference between the scalar and vector formulations of a moment. Let's consider a 50-pound force directed in the vertical direction at a distance of 5 feet from the horizontal axis that passes through some given point A. The moment then that this 50-pound force produces about point A is the product of the magnitude of the force times this perpendicular distance between the line of action of the force and the axis that passes through point A. And the sense of rotation is counterclockwise, which we designate as being positive. So this is the notation that we use, a plus sign with a arrow pointing in the counterclockwise direction designating a positive moment, that any moment's calculated in this sense. And then we utilize the m for the moment and the subscript a to designate the point about which we're calculating the moment. The plus sign is put in just taken from the sense of rotation that we pick off of by looking at the diagram itself, not from the sign of the perpendicular distance or the sign of the magnitude of the vector. And then we have the magnitude of the force vector, the magnitude of the perpendicular distance, and the product then of 50 pounds times 5 feet produces a moment of 250 foot-pounds. If we have a slightly different vector, in this case a 50-pound force, but now at an angle such that it has both a y component and an x component, in this case 40 pounds and 30 pounds respectively, we see that the y component of this vector, again, it has a line of action that's parallel to an axis that passes through point A, and it has a moment arm of 50 feet, whereas the 30-pound force component has a line of action that actually passes directly through point A, producing a 0 moment arm. So in this case, the original 50-pound force vector can be replaced by its Cartesian components, and we find out that keeping both components in our calculation here, we find out that the 40-pound force would indeed cause a counterclockwise rotation, so it has a positive designation and the magnitude of 40 pounds times its moment arm of 5 feet. Now the 30-pound force we bring in here, I'm just going to use positive because it doesn't matter here, because it has a moment arm of 0 feet. So I'm just putting in here for completeness, but we find out that even though this is a 50-pound force, the magnitude of the moment only comes from its component that's 40 pounds. So 40 pounds times 5 feet equals 200 foot-pounds. Now if I take that same vector and move its point of application off of the horizontal axis that passes through the point of interest, we can again break this force into its x and y components, and in this particular case we find out that the y component has a perpendicular moment arm of 5 feet, whereas the horizontal component of 30 pounds now has a moment arm of 3 feet. Now what we're going to find is that when we look at the sense of rotation of the 40-pound force with its moment arm, is that its sense of rotation is counterclockwise, and we get a positive sign, and the moment produced by this component of the force vector is 40 pounds times its moment arm of 5 feet. Now the 30-pound force acting from left to right at a point above the line of action of point A ends up producing a clockwise sense of rotation. So then it comes in with a negative sign, and the magnitude of this component of the moment is 30 pounds times 3 feet. So the 200 pounds minus the 90 foot-pounds rather equals a total moment of 110 foot-pounds. Now we can take the exact same setup, but in this case we can create a vector formulation. So we look at the position vector that goes from the point of interest, in this case A, to the point of application of the force, and we designate that position vector as R, A to B, and it has a 5i plus 3j. position vector. Now what we can do is we now use the vector definition of the moment. So we take the moment about point A equals the cross product of the position vector with the force vector. In this case, we can write it out, and this is the position vector 5i plus 3j crossed with the force vector of 30i plus 40j. Now, to calculate this, we can just do a straight expansion of this cross product. So 5 times 30 with I cross I, and 5 times 40 with I cross j, etc. Now what we find out, of course, is that the I cross I and the j cross j components are 0, whereas I cross j produces a k unit vector, and the j cross I produces a negative k, where I remind you that the k unit vector points in the positive z direction. So we can then rewrite, or we can finish the calculation, and we find out that the 5, so this is 0, 5 times 40 is 200, I cross j is k, 3 times 30 is 90, j cross I is negative k, and again the 3 times 40 with the j cross j equals 0. And we find out that the total moment about point A in vector form is 110 foot-pounds, but it points in the positive k direction. And if you would put your thumb pointing along the z-axis and curl your fingers about point Z, you would find out that the sense of rotation is counterclockwise about this point A. So looking at that, this is the representation in vector form, and this is the representation in scalar form. And using the vector formulation, we found out that the moment about A is a vector of a magnitude 110 foot-pounds with a direction in the positive z direction. And the scalar formulation is the moment about point A designated as counterclockwise in the positive direction, and again it's 110 pounds. So they are equivalent to each other, and one is a vector formulation and the second is a scalar formulation.